In this lecture, we're going to do a quick review of pointers and then go into some pitfalls with pointers that you need to be aware of as you do the lab tomorrow and for the rest of this week. So if you remember, a pointer variable is declared by putting a star in front of the variable, and then you can assign an address to that variable using the ampersand character. So ampersand x in this case says assign to p the address of x. So for example, if memory looked like this, where p is at location 1000, hexadecimal 1000, and x is at hexadecimal 1004, then p currently contains the address 1004, which is the address of x. If you want to dereference a pointer, so dereference a pointer, you do that with also the star operator. So if I say star p equals 8, I'm saying I want to assign 8 to the variable to which p points. Well, in this case, if we look at the the value of p, it's 0x1004, meaning it points to x, and therefore 8 would be assigned to x. Similarly, we could say something like int y equals p plus 4, and y would get the value 12 in this case, because we would go to the variable to which p points, x, extract its value 8, and add 4 to it. Now, when you're also allowed to create pointers to anonymous memory, that is, memory that is allocated from what we call the heap. So I could say int star p equals new int, and that would allocate a new piece of memory and return the address of that memory. Remember, that memory comes from what we call the heap. So whereas the stack is growing from the bottom of memory, the heap is coming down. So this memory, for example, might be, say, 0x2000 that we get back. So now we might have p with 0x2000. Now, typically this memory is uninitialized. However, if I had instead said new int 10, that would have initialized the value of that memory to be 10. You're also allowed to delete anonymous memory. So we call this object that we have just created, we often call it an anonymous object or anonymous variable, because you can't refer to it by a name the way you could x or y. The only way you can get at it is through a pointer. So you can also say delete p, and what that does is it finds the memory address which p stores. In this case it is 0x2000, and it deletes the object assigned to that location. So in this case it would delete the integer that had been allocated. When you use pointers, you need to be careful that when you allocate objects, if you no longer need them, that you deallocate them. Otherwise, you get a memory leak, which we will talk about shortly. Now, a very useful thing with pointers is that they can be made to also point to objects. So for example, if I have a class hash table entry, and let's say it was public. Remember, we say we don't normally want you doing it, but for convenience, I'm going to make these public. Key is a string. Let's say that a value is the integer. And let's say we wanted to create a vector of these hash table entries. Often what we would do is we would create a vector of pointers to these hash table entries. And we would in order to add entries to this table, we would have to declare a variable, say new entry. And we might read some information, say, from a file. So let's say we'd read some information in a file and we'd read them into a value. Let's call it age, and let's say this key is going to be a name. So let's say we read values into age and name. That's what I'll do with ... And then I might have new entry equals new HTE. And this is going to create a new hash table entry. Notice I put the bracket or parentheses after it to indicate it's calling the zero argument constructor. And then I could assign name to the key field. And notice I used an arrow rather than a asterisk here. So this is another way to do dereferencing. So let me just finish up by saying new entry value equals age. So what the arrow here is doing, it's like a dereference operation. It's actually just like saying new entry with the dereference, then in parentheses dot key equals name. And it's just more syntactically pleasing to look at the arrow than to look at this notation. This notation says dereference, returning the anonymous object that new entry points to, and then I had to put in parentheses because of the way operators bind. So that made it clear I wanted the anonymous object and then I wanted its key field. But we typically use these arrows when we're dealing with objects. And then we could add this pointer to the table by pushback. And now the table would have a pointer to it. So how might that actually look? The way it might actually look is here's table, and right now it has only one entry in it. And it's going to have, let's say that the memory that was given to that new entry was 2000. So here on the heap, yet 0x2000 is the entry for that was allocated, the hash table entry that was allocated. So 0x2000, we have a pointer to it from this vector of hash table entry pointers. And just quickly, so that we are all on the same page, when dereferencing, use star for pointers to primitive types. And use the arrow for pointers to objects. And specifically, you use the arrow to get at the fields of the objects. You would also use it to get to methods if you're going to call a method associated with a particular object. So now I just want to quickly go over some pitfalls with pointers because they are many and they can cause you woe. So the first pitfall is a so-called uninitialized pointer. So for example, when I say int star p, I have an uninitialized pointer. We have no idea what it points to. If I try to say star p equals 10, I'm likely to get something called a segfault because I'm probably trying to access a piece of memory that's invalid. Most likely P has the value 0, and 0 is an invalid memory address. So we need to make sure that we always initialize a pointer before we assign a value to it. So for example, we might have said here P equals new int. Okay, so that comes, now we come to our second kind of error. So let's say we now said int x equals star p. Well, the second thing is that we have uninitialized value for an anonymous object. You'll see that we actually never assigned a value to our new piece of memory. We created that new piece of memory right here, but we never assigned it a value. So when we try to assign the value of that memory to x, we don't know what it is. So you need to be careful to initialize your memory, initialize the value of memory before using it. The third pitfall is something we call a memory leak. Sometimes you'll also see it referred to as a lost object. That occurs in one of two cases. If a pointer, the only pointer to the anonymous object, goes out of scope, or if the only pointer to an anonymous object is made to point to another object. Okay, so here's an example with the first one. Let's say we have, let's make an example of where the pointer goes out of scope. Let's say we have int main, and we have int x, and we now create another scope. I understand we wouldn't often do this, but I'm doing this for the sample problem. P equals new int, and P equals 10, so we initialize it. And now we come out of here, and we might have x equals 20. While you may not notice anything funny, what happened when we came out of this block right here is that P went out of scope, because it's only in scope when it's between these two braces. Therefore, P went out of scope and we lost the pointer to this piece of memory. It's now a lost object. There's no way to get access to it because there's no pointer to it. A more common problem is that you might do the following. You might say int star P equals new int. And so perhaps P gets a pointer to memory location 2000. Okay, so we have basically P points to that memory location. Now we say P equals 10. We assign 10 to it. Now we're going to do a new int. So now P is made to point to a new integer, and perhaps it gets a new value like 2004. Well, we just lost the only pointer to this old piece of memory. So we have a memory leak again, or lost object, because we can never reclaim this piece of memory. So before we actually assign the new int, what we need to make sure we do is say delete P here. This delete will will deallocate the old memory object, namely this one, give it back to the heap so that it could be given back again at some later point in time. So that covers the two types that we had, a pointer to the anonymous object going out of scope, or the only pointer to an anonymous object being made to point to another object. So again, here we could have prevented our problem by having delete P at the end of our scope, and then it would have gotten rid of that memory. It would have cleaned it up. The last type of pointer pitfall that you're going to have to worry about is the dangling pointer. And it occurs when a pointer points to a deleted anonymous object. So for example, let's say that we had int star p equals new int, and we had int star q equals p. So now we have a situation where both p and q point to the same piece of memory. Now let's say we do delete p. So this piece of memory right here is given back to the memory system, but you'll notice that q still points to it. So something, p may or may not point somewhere. We don't know what happens with p, but we know for sure that q is pointing to a piece of memory that's been given back to the memory system. That is, it points to a deleted anonymous object. And if we now do something like, say, q equals 20, we're on very shaky ground because we're accessing an object that has been given back to the memory system, and that piece of memory is eligible to be given out again using the new operator. So if that memory had already been given out using the new operator, then Q is changing someone else's memory in a way that's unexpected and is likely to lead to a segmentation fault. So dangling pointers are your fourth pointer pitfall. It's when you prematurely delete an anonymous object before while there's still other pointers out that point to it. So that covers the basics with pointers. And on Thursday, we're going to go through the rest of the pointer notes and work through a couple examples in class.